Okay, so yeah, so I hope my audio is still clear.
Yes.
Yes, sir. It is.
Okay, yeah. Right. See, what we'll do is we have 2 hours. We have to cover diagonalization, this test for diagonalizability, Fibonacci sequence, and one more section. Okay, so that will be our target. There were few small points that I missed out last time. So first 5 minutes, what I'll do is I'll quickly go over the first four topics very briefly. I'll just breeze through them, and then uh, from there I will take up these four topics. Okay, by that time I think others can also join. So this will be the list of topics. So linear transformations, I'm not going to go into any detail. It's just a linear map from a vector space to another. We'll basically be looking at those maps from R2 to R2, right? So a linear map is completely specified if you know what happens to the basis vectors, right? And this is what linear transformation looks like, right? The action it has on the vectors on the space of vectors that you have. This is a rotation matrix. The one you saw before is a scaling matrix, right? And this is rotation cum scaling. This is nothing but composition of two linear transformations that we just saw, right? So this is some kind of a shear. Okay, so that was about linear transformations, and from there uh, yeah, so from there we went to the concept of eigenvectors and eigenvalues. So eigenvectors basically are those vectors whose direction is preserved, for whom the direction is preserved before and after the transformation. So for example, -1, 1 and 1, 0 in this case are eigenvectors, and because that direction is preserved, as you can see, after the transformation. So eigenvalues are nothing but the amount, the factor by which the vector is scaled, right? By which an eigenvector is scaled. So the equation that you should remember always is that this TV equal to lambda V, then V is an eigenvector and lambda is its eigenvalue, right? And together they are called an eigenpair. You can never separate the two; they always come together. Okay, so whatever holds good for linear transformation holds good for a matrix because they are essentially the one and the same object but in different contexts, right? So yeah, so eigenvectors, remember they should always be non-zero. They can never be zero. Okay, so the eigenspace, if you remember, is nothing but the set of all so all the non-zero vectors in an eigenspace will be the eigenvectors corresponding to some eigenvalue lambda. Okay, so I am not going into the details. This is something you already saw. So if you, in case you want to know, you want to study more about them, or if you want to spend some time on these slides, you can always go and access this link, right? It's there in the MLF notes page. So you have to just click on slides and you will be able to get hold of it. Okay, so
Sir, one more small question, sir.
yeah.
In the eigenvector, sir, we know, the vector after the linear transformation, those vector who do not change its direction, we call those as an eigenvector.
Right.
Now, my question, if the vector is just flipped 180 degree, so it's pointing towards -1, 1. Now it is shifted to 1 -1. Then that is belongs to eigenvector because
Yeah,
that is
that is
in
also
same
eigenvector.
line, but its direction is
Yeah,
just
correct. That is also an eigenvector. So the reason is because if you say what the case you are talking about is that you have a vector v, and on after transformation it becomes -v, right? So this is the same as lambda times v, where lambda equal to -1, right? So lambda is -1. So this is still an eigenvector with eigenvalue -1. So the direction, maybe that is the wrong word to use. The resulting vector after the transformation should either be parallel or anti-parallel.
Yeah. Okay.
right? So that is
Okay.
the
Okay.
okay, right? So eigenvectors and eigenvalues. So even if you don't remember anything that I showed you so far, one thing that you need to know is this equation TV equal to lambda V or AV equal to lambda V. So as long as you know that, it's enough. So how do we find the eigenvalues of a matrix A? As we saw before, you start with something like this: AX equal to lambda X, and then you do some algebraic manipulations and you end up with this equation A minus lambda I times X equal to 0. Then we saw that there are some arguments that you can make, and finally you will end up with something like this, which says that the determinant of A minus lambda I should be 0. So this this is what is called, this will result in a polynomial in lambda. Okay, if you want an example, then look at this matrix A. So determinant of A minus lambda equal to 0 will give you this, right, which will give you this polynomial in lambda. Here it's a degree 2 polynomial. So lambda equal to 2 and 3 are the eigenvalues. Okay, so in general for an n by n matrix, this this will factor into n such monomials, right? Monomial, I hope you remember what it is. Just degree 1, right? So lambda 1 minus lambda into lambda 2 minus lambda, so on till lambda n minus lambda. Okay, so this expression on the right hand side is what is called the characteristic polynomial. Every matrix will have one polynomial. Okay, so some properties, one property only we saw last time. The other property is this: the sum of the eigenvalues is equal to the trace of the matrix. So do you all know what the trace of the matrix is?
Yes, sir.
Okay, right. So the trace, in case some of you are not aware, is the sum of the diagonal values.
Diagonals.
Right, yeah. So that is the trace, right? So the sum of the eigenvalues is equal to the sum of the diagonal elements of a matrix. Okay, the second property is that the product of the eigenvalues is equal to the determinant of the matrix. So these are two properties that will be routinely asked in the exam, right? So you must know this. Okay, so if you just going back to this to see why these properties are true, if you look at this, the sum of the diagonal elements is 5. So that is equal to the sum of the eigenvalues 2 plus 3. So the determinant is what? 3 into 2, 6 is the determinant. The product of the eigenvalues is 3 into 2, 6. Okay, so these are two very simple properties, and which you have to know. Okay, this is just some proof for that, which I'm skipping. You can refer to the slides later. So I think we stopped there. No, we also did this part. Once you have the eigenvalues, how do we compute the eigenvectors? I think we covered this part also. Very quickly, I'll go over that. So if lambda equal to 2 is an eigenvalue, how do you find the eigenvectors? You solve this equation, A minus lambda I times X equal to 0. Right? So you end up with an equation like this. So eigenvector could be -1, 1 or 1, -1 and variations of it, right? So -1, 1 is one such vector, and if you want all such vectors, you can just take the span of -1, 1, right? So every non-zero vector in this span will be an eigenvector with eigenvalue lambda equal to 2. Okay, so yeah, so till this we saw in the last in during Monday's session. I hope there are no questions till this point. Are you all clear till this?
Yeah, only the first
Yes.
line I didn't understand that day also. I watched that video. That first line.
This one,
yeah, it's an eigenpair. Can you just
Okay.
explain briefly the first line?
Yeah, so what I mean by that is so when I say that lambda comma v is an eigenpair, then means v is an eigenvector of A with eigenvalue lambda. So AV equal to lambda v. This you are clear, right?
Yes. Yeah.
So if AV equal to lambda v, then what I do is I do some small tricks. That basically you can multiply both sides by I, right? Identity matrix.
Yes.
So and I times A is just A, so I'm just going to ignore this I here. So I have AV equal to lambda I times V, right? So now what I do is AV minus lambda I V equal to 0. I come till this part. Then see, A is a matrix, lambda times I is a matrix, right? So A is a matrix, lambda times I is a matrix. So what I do is I just take the matrices out, or rather I take V out. So A minus lambda I into V equal to 0, right? So this is what we are really talking about, right?
Yeah. Yeah.
So once A minus lambda I times V equal to 0,
So V is
that
in
is,
null space. Is that
yeah,
so?
right.
Okay.
So V is in the null space of A minus lambda I. So every non-zero vector in the null space of A minus lambda I is an eigenvector with
Yeah.
eigenvalue lambda.
Yeah.
Sir, how come V belongs to the null space?
How come we?
Okay. Of A minus lambda I. Yeah.
Right? Yeah. Okay. Any other questions?
Yeah, sir, can you please explain the last point once again? Span of B is nothing but the eigenspace corresponding to lambda.
Yeah. So see, once you reach this point, A minus lambda I times V equal to 0, you essentially you are looking at what? You are looking at the null space of A minus lambda I, right? So all the eigenvectors will be in this null space. Okay. Is that part clear? So once that is clear, then what you need to do is essentially see this, that null space is a subspace of a vector space, right? So assume that we are talking about Rn, then A minus lambda I is null space of A minus lambda I is some subspace of Rn, right? So it will have one basis. You call that basis B. So I can now write span of B equal to null space of A minus lambda I, where B is a basis for this subspace.
Yes, got it.
Okay, so that is what this is. If you want to know how to find the basis of a subspace, you can refer to week 3. Week 3 there is one set of notes for that. You can refer to that.
Yes, I got it, sir. Thanks.
Okay, so
are these things available in our dashboard?
These are not available in the dashboard, but I can we'll paste the link in discourse. In fact, this link is there in discourse. You have to just go and look at this section called slides in the MLF notes, and inside that in links you have week 4 computing eigenvectors, right? So that is okay. So we are here. Okay, so this is where we are. Till this point we completed in the last session. So now we'll take up the remaining parts, right? So we start with this topic called diagonalization.
Yes, sir.
Yes, sir.
Okay, so so diagonalization. So we'll take the diagonal part out and see what it means. So diagonal matrices are interesting. Okay, so interesting from the mathematical standpoint, not in a general sense. For mathematicians, they are interesting, and we hope to see why they are interesting in a while. So consider any diagonal matrix. Okay, it is of this form. A1 to AN are the diagonal elements, and rest are all zeros. I have not displayed the zeros. So you can also write this as diag of A1 to AN. Okay, so this is a simpler representation. Since you need only n numbers to specify a diagonal matrix, you get rid of all the other noise, and you just represent it using these n numbers. Okay, so we look at a series of properties of diagonal matrices. This is the first property. D. So I have taken a 3 by 3 matrix to keep things simple. Okay, so DE1, DE2, DE3. Okay, so can someone tell me what E1, E2, E3 are really here?
Standard basis vector.
The
Okay,
basis.
Yeah, right. They are vectors from the standard basis, right? So E1, E2, E3. Okay, so each of this is a matrix vector product, right? So what do you think will be the result of the multiplication in each of these three cases?
First
First
column,
one will give us
second column,
A1,
and third
second one
column
will be
of
A2, and
D.
third one will be A3.
No, first column of matrix D, second column of matrix D, and third column of matrix D.
Okay, first column, second column, third column. Okay, that is right. First column of matrix D, second and third. Okay, is there any is there a simpler way to write these three products? I mean, is there a simpler way to write this RHS?
The linear combination of
Of E1, E2, and E3.
Okay, can you tell me what the first what should come here?
A1, E1
Okay, A1 E1.
plus A2, E2 plus A3, E3.
Okay, is it plus or
No, I'm sorry. I like three individually, A1, E1, and then for second one it will be A2, E2, and then for third one it will be A3, E3.
right? Okay, so it will be A1 E1, A2 E2, A3 E3, right? So far so good. So what can you infer from the slide?
That A1 is the eigenvalue for D
Okay, with eigenvector.
with eigenvector E1.
Okay, right. That's good, right? So I hope all of you see this inference, right? So E1, E2, E3 are eigenvectors corresponding to eigenvalues A1, A2, A3.
Right.
Right. So what is the first property of a diagonal matrix then?
That in the diagonals we can just read out the eigenvalues.
Correct. And the eigenvectors are
Eigenvectors are
standard basis.
standard basis, right? Okay. So this is the first property. The first property is this, namely the eigenvalues of a diagonal matrix are the diagonal elements. The elements or so the vectors in the standard basis are the eigenvectors. Okay, and the correspondence is clear to you, I think, right? So if the ith diagonal element is AI, then EI is the corresponding eigenvector. Okay, so this is property 1. I hope everyone is clear with this property.
yes.
Okay, we'll move on to property 2. So what is the product of two diagonal matrices?
A1 square,
Simply,
A2 square,
yeah.
A3 square.
Okay, A1 square,
Another
A2 square, A3 square, right? So what about the kth power?
A1 power k, A2 power k, A3 power k.
Okay, right. So this is this seems simple, but it's a very powerful property. So we'll just write that down. What does this say? So in English, so we'll write it. We won't use notation. What we'll say is that so raising to a power is easy, right? So it's a very naive way of saying it, but that's what the property means, right? If you want to raise a matrix, a diagonal matrix to some power, it is very easy. Computationally, it's very easy. You just need to raise n numbers to the kth power. Okay, so that is the second property. So what is the determinant of diagonal matrix?
A1, A2, A3.
Right, so that is A1, A2, A3. Okay, so property 3 is that the product of the diagonal. Okay, right? So these are the three properties. Now, so when is a diagonal matrix invertible? When does it have an inverse?
When A1, A2, A3 are non-zero.
Okay, that's correct. So let's assume that A1, A2, A3 are non-zero, in which case the inverse will be just the reciprocals, right? Is that right?
Yes, sir. Correct.
Okay. So a diagonal matrix is okay. So if a diagonal matrix has non-zero elements, okay, then it is invertible, right? So that is what we have seen, and the inverse is just the reciprocal of the diagonal elements. Okay, so these are four properties, and so the claim I'm making is that these are very good properties for a matrix to have. Okay, or as good as it gets, right, for a matrix. So why do I say that? So can someone back up this claim? So when I say that these are good properties to have, so for example, this invertibility, right? So why is it such a good property? This inverse being just the reciprocal of the diagonal elements. Why do you think that's a good property to have?
It will help
Sir?
us to solve equations.
Okay.
Sir, we don't need to calculate adjoint and all that to find inverse.
Right. So computing the inverse is computationally expensive, right?
Yes.
So you don't want to spend so much of computation in finding the inverse, right? So if you have a diagonal matrix, then so from a computational standpoint, so what is the complexity of this operation? Assuming some of you have done PDSA, if you have an n by n matrix to compute the the inverse of a diagonal matrix, what would be the complexity of an algorithm that you would write?
N square.
Sorry?
N square.
Square, sir.
Maybe n square.
Okay. N by n, right? So n by n is the matrix. So, sorry? Okay. So how, if you have three elements, how many operations do you have to do to get the inverse?
3.
Yeah. So it's just linear, right?
Mm.
So it is just linear in the in number of rows of the matrix, right? So I have only, if I have an n by n matrix, assuming that I have already taken the matrix as input, okay, then you just need to find the reciprocal of n numbers, right? So computing the inverse is therefore just linear in the number of diagonal elements. Okay, so yeah, that's why inverse is a good property to have. And determinant, likewise, it's you all know how messy the computation can get for a general matrix. We'll see a direct application of the d power k, right, in the Fibonacci sequence that we'll take up. The other part is a very crucial property which we'll be using right now. Okay, so remember this property which states that if you have a diagonal matrix, the diagonal elements are the eigenvalues, and the elements from the standard basis are the corresponding eigenvectors. So we'll use that property now.
So one question, sir.
Yeah.
So just the last page means hold on, sir. So this D is some linear transformation because it is matrix.
Correct. Yes.
Now this D inverse means I am backing where if I apply D inverse on D means I am just reversing me to my original position.
Right.
Correct. Yeah.
This D inverse mean it's right. Like I am having some linear transformation. My D inverse apply means I am go back to my original position.
Yeah. So you start off with a vector D. As you start off with a vector V, D times V will give you some vector, and then you D inverse of that D times V, you will go back to the vector V.
Original vector. Okay.
Original
Okay,
vector.
sir.
Yeah.
Okay. Okay.
All right. So any other questions so far?
No.
Okay. So this is the setup. Okay. So for in order to study, so remember that we are studying this concept called diagonalization. Okay, so we are going to come to right. So diagonal matrices have excellent properties as we have seen. So this is our hope, right? Our hope is that okay, all matrices are not diagonal. Can we hope that can we hope that we can find some matrices which are somewhat related to a diagonal matrix? Okay, so it's like recent, I mean, like few years back, right, when Sundar Pichai became CEO of Google, what people used to do, at least after knowing the news, was that somehow they tried to associate with him. Okay, I went to the same school as Sundar Pichai. I am also from IIT Kharagpur, right? So something similar happens in the case of matrices, right? Diagonal matrices have excellent properties. Can I hope to be associated with a diagonal matrix? Right? This is the question that we are asking. Okay, so diagonal matrices are not necessarily diagonal, yet they are very closely related to them. What are they and how are they related to diagonal matrices? So this is what we'll be studying in the next few minutes. Okay. Okay, so can you please fill in the blanks here? Blank.
Eigenvectors.
Okay. Is that right? Everyone?
Yes.
Okay, right. So vectors in the standard basis are eigenvectors of a diagonal matrix. So we are going to use this property. Okay, now let's think about any general n by n matrix. Okay, and we are going to impose this condition, right? We are going to impose this condition that A has n linearly independent eigenvectors. Okay, in general, a matrix need not have n linearly independent in general, a matrix need not have n linearly independent eigenvectors at all. Okay, but we are going to assume that there is some matrix A for which this happy condition is satisfied. Okay, so do you all agree that beta equal to this set of V1 to Vn will be a basis for Rn? Is there anyone who's not in agreement with that? Okay, I hope all of you agree with that.
Yes, sir.
Okay, then we have a basis of eigenvectors of A. Right, so I'll just stop for a minute here. Do you all understand whatever is there on the slide?
Where does the assumption come from? Like
this set beta?
This condition that you have taken yourself, right? For now.
Okay. You are asking why am I taking this condition? Correct. Okay. So the reason I'm taking this condition is that I know that for a diagonal matrix, the eigenvectors are in some sense basis vectors, right? This is something I know. For a diagonal matrix from property 1, I know that the eigenvectors are elements of a basis. Okay, perhaps if I use that property, then I might be close to a diagonal matrix. That is why I impose this condition.
Sir, for a diagonal matrix, generally the eigenvectors are even E2 up to En, right?
Always, right?
Those
so for
with,
yeah. Correct. Yeah.
But it like the entire dimension of the domain space will be covered by eigenvectors. So for that, we are saying that it will have up till n, right, sir? So
yeah. Right. See, I'll again state what we are aiming to do. Right. We are looking for matrices which are very close to diagonal matrices. Okay. We all matrices are not diagonal, so that is something we have to live with. But we are asking if we can get close to them in some way, right? So remember that example that I said before. We want to get close to some person, so we at least try to mimic some attributes of that particular person. Okay, so maybe we went to the same school, right? So we share some attribute or property which is in common with that other person, and then we feel happy because of that, right? So likewise, the property that I want to share with a diagonal matrix is this: eigenvectors belonging to a basis, or eigenvectors forming the basis, which is what this condition is really. Okay, can I go ahead? Is everyone okay with this condition?
Yes, sir.
Okay.
Yes, sir.
All right. So if you're all okay with this condition, then we have a basis of eigenvectors of A, right? And that is where we come up with the first definition for a diagonalizable matrix, right? So an n by n matrix A is diagonalizable, right? If there is a basis of eigenvectors for Rn. Okay,
Yes.
so the term diagonalizable, you can think about it as something that is similar to a diagonal matrix, right? Something which is very close to a diagonal matrix, but which is not necessarily diagonal. Okay, so this is the first definition. If you have a matrix A whose eigenvectors form a basis for Rn, then that particular matrix is diagonalizable.
Can you give one example?
Yeah, we'll come to that, right? We'll come to the examples part. I will for now proceed with this, right? So main question that many of you might ask is, okay, so what? Okay, so what's the use of this definition? Okay, so assume that you have a 3 by 3 matrix. Assume that you have some 3 by 3 matrix A that has 3 eigenvalues, lambda 1, lambda 2, lambda 3, and corresponding to that you have 3 eigenvectors v1, v2, v3. Okay, and these 3 eigenvectors satisfy this condition, right? They form a basis for R3. Okay, v1, v2, v3, they form a basis for R3. So this is according to the definition diagonalizable. So we are exploring the so what part here. So what? Okay, I'm just rewriting this in this form: A times v1. V1 is a column vector, right? Ultimately, so I'm just expanding it like this. Lambda 1 v1, I'm just writing it this way. You will see why I'm doing this. And that helps me write it in the form of a single equation. So did you all see the jump from the previous slide to the current slide? Is this transition okay with everyone? Anyone who is not sure why this happened?
Didn't get it, sir.
Okay. This part is clear. A v1, lambda 1 v1.
Yes, sir.
Okay. So see, for this you need to know matrix vector multiplication. So let me okay, see, there are several ways to multiply a matrix and two matrices, right? So there are several pictures. There is one in particular which is called a matrix column picture. Okay, so if you have two matrices, right, A and B, A is some m by n matrix and B is some n by p matrix. Okay, so if you write B as a sequence of columns, right, v1 to vp, so there are p columns. So A times B is actually equal to this matrix A v1 so on up to A vp. So it's like you multiply a matrix and a column vector, you multiply a matrix and the column vector, so on p times. Okay, so are you familiar with this view of a matrix product?
Yeah. Yes, sir.
Right, so this is what I'm doing here. This is what I'm doing here. So basically A times V1 is lambda 1 V1, A times V2 is lambda 2 V2, A times V3 is lambda 3 V3. Okay, so this is one way of multiplying two matrices. Assuming that this is clear, I can now rewrite the RHS this way. Is this clear to everyone?
Yes.
Okay, so V1, V2, V3, and then this is just a diagonal matrix. So this is not clear. You can go and work it out. So it's not too hard. So this again, if you spend a little while, you will be able to figure out why this thing works, right? How you can decompose this into this. Okay, so at this stage, remember that V1, V2, V3 are what?
Eigenvectors of A.
Okay, eigenvectors of A. In addition, what are they?
Basis of Rn.
Yeah, they are a basis for R3, right? So remember the condition that we started off with. They are eigenvectors and they form a basis. So what I'm going to do is I'm going to call this matrix Q, right? This is some 3 by 3 matrix Q, and this is some diagonal matrix D consisting of the eigenvalues of A, lambda 1, lambda 2, lambda 3. Now, what property does this matrix Q have?
It is invertible.
Yes, good, right? That's a very important property. Why is it invertible?
Because V1, V2, V3 are linearly independent.
Exactly, right? So V1, V2, V3 are linearly independent, therefore it is invertible. Okay, so I'm just rewriting this as AQ equal to QD, right? I'm not doing anything extra here. I'm just making use of this matrix Q. I'm just calling it Q here, D. So AQ equal to QD can be now rewritten as what? Can I simplify? I mean, not simplify. Can I rewrite this right hand side in some other way?
Yeah, Q inverse AQ equal to D.
QD
Good.
Q inverse.
Good. Both are correct. I'll take one of these two versions. I'll express it this way: A equal to Q D Q inverse. Okay. So is it clear to everyone?
Yes, sir.
Yes, sir.
Okay. So what we have done is we have started with the diagonalizable matrix A. If A is
Sir, if possible, can you explain with an example?
yeah.
Okay, sir.
So this is what we have arrived at, right? If A is diagonalizable, then A equal to Q D Q inverse. Okay, so the example will come. Don't worry. We will. So when we take up this part, right, on Fibonacci sequence, we'll actually show the full example. Okay, so
We have taken the normal matrix and converted it into diagonal matrix. That's what we have done here, right?
We have
The
some
matrix conditions, of course, with that linearly, eigenvector with condition. Then we have converted to a diagonal matrix.
yeah, so I wouldn't say that we have converted, but we have showed that there is a relationship with the diagonal matrix, right? So this is what we started off with. Our hope was that to see if A is somehow related to a diagonal matrix, and we have shown that, right? A is similar to a diagonal matrix, where I use the term similar in a very specific sense. So I'll just continue and it will become clear. So this is the definition, second definition, right? An n by n matrix A is diagonalizable if it is similar to a diagonal matrix. So do you all remember from Max 2 what similar matrices are?
Yes, sir.
Yes, sir.
Okay, can you tell me when are two matrices similar?
If there exist
Same rank.
Same form, like Q is equal to A, D, A inverse, then Q and D are equal.
Okay, right. So I'll just state it here. This is from Max 2. right? So similar matrices. So two matrices A and B are similar if there exists some invertible matrix Q such that
So you have written A there.
Sir, did you mean invertible matrix Q?
yeah, sorry. Okay. So is that right?
Yes, sir.
Okay, so this is what we mean by similar matrices. So this is again very algebraic definition, but we have to live with this. So what we have here is A equal to QD Q inverse. So A and D are similar. Okay, Q is invertible. So this is the second definition of diagonalizability, or when is a so what is a diagonalizable matrix? It's something which is similar to a diagonal matrix. Okay, so that is definition 2. See, examples will come to it, but at present, I hope you get the picture of what we are talking about. Yeah. So see, some properties again. So properties of diagonalizable matrices this time. Okay, so the question we have to ask now is, do diagonalizable matrices have some of the properties that we saw for diagonal matrices, right? If they don't have, then there's no point in a matrix being diagonalizable. So I need to have some properties, or at least I need to be close to some properties that D has. Okay, so we look at the first property. We look at the eigenvalues of A first. Okay, so to get the eigenvalues of A, we just have to solve for this determinant of A minus lambda equal to 0. So I just substitute Q D Q inverse here. Okay, so can someone tell me what the next step could be? How do I proceed from here?
A is equal to D.
A is not equal to D, right? A is Q D Q inverse. So I have substituted that. Now I want to simplify the RHS further. Can anyone suggest some ideas?
Can we write
You
it?
can separate the determinant using minus a.
Can we write lambda I as Q lambda Q I Q inverse, and then we can take the Q D minus lambda I and then Q inverse.
Good. That is what we are going to do, right? So since Q is invertible, we are just going to replace I as Q inverse. Okay, so I mean, yeah, Q inverse would have been better, but yeah. So now notice that there is a Q to the left of D and Q inverse to the right of D. Likewise, here you have a Q to the left of I and Q inverse to the right of I. So I can just do this kind of a decomposition, right? Q times D minus lambda I into Q inverse. Okay, is this part clear? Okay. Now what is the next step?
Just spread out the determinant sign, meaning determinant of Q into determinant of D minus lambda I into determinant of Q inverse.
Right. So product of determinant of products is product of determinants. So we make use of that property, and we'll end up with what? What would be the final step?
Determinant of Q cannot be equal to 0. So in order for having determinant of A minus lambda equals to 0, we need to have determinant of D minus lambda equals to 0.
Right. So the other way of looking at it is these two get cancelled, right? So Q inverse and Q will vanish, leaving us with
determinant D minus lambda.
Right. So what this is saying is that the eigenvalues of A are the same as the eigenvalues of the diagonal matrix. Right?
Yes, sir.
So there is some use after all in diagonal in a matrix being diagonalizable, because the corresponding diagonal matrix, whatever eigenvalues it has, this fellow is going to have the same eigenvalues. Okay, so this is one property. Maybe may not be so interesting, but property 2 is very useful, which is what happens when you raise a matrix, a diagonalizable matrix, to the kth power. Okay, we'll see what happens. So this is QD Q inverse power k. So I just have k blocks of QD Q inverse. So what will happen?
So it will be QD to the power K.
Most of them will go to I, Q inverse and Q.
Right. So most of them will go to I. So I just, so did everyone understand this part? If not, we'll work on this. Is there, does anyone want an extra explanation here? Or is this clear to all?
Yes, sir.
Yes.
Okay. All right. So the nice part is it's very easy to raise a diagonalizable matrix to the kth power. Right. So you just need to raise the middle diagonal matrix to the kth power. Okay, so the summary from this part is that a matrix A is diagonalizable if Rn has a basis of eigenvectors of A. That is one definition. And the second definition is that A is similar to a diagonal matrix. Okay, so these are the definitions for a diagonalizable matrix, and that is the end of one section. Okay, any questions, or shall we move on to the next part?
Move, sir.
Okay. All right. So I know that this will be dry for some of you, but there's no helping it. Unfortunately, that's how it is.
I have a question.
Yeah.
So what is the purpose of learning this?
Sorry, what is the
purpose?
Yeah. So the purpose of learning this is so that you will be able to do something called SVD, singular value decomposition, and something else called principal component analysis. These are both techniques to understand data. So all this is needed if you want to understand data better, right? And data is at the heart of ML, right? So there is a lot of foundation that needs to be laid before you can understand those two methods. And these two methods will be discussed only in week 6. So all this heavy duty algebra is required for that. We can skip all this and directly jump to those two methods, but then there would be no fun in that. I mean, okay, might be interesting to just skip to that, but it'll just be a black box, right? I mean, you'll just be using it as a black box, and you wouldn't be able to actually play around with that technique, right? Okay, so we saw all this. So this is where we are now. So just give me 1 minute. So what do you think? Are all matrices diagonalizable?
No, sir.
Okay, so not all matrices are diagonalizable. So let's take an example. Okay, so this is some matrix, 2 by 2 matrix. Let's go and find the eigenvalues. Okay, so this is the characteristic polynomial that you get, lambda square plus 1. Okay, so a minus lambda is just minus lambda 1 minus lambda. So the determinant is lambda square plus 1. So what are the eigenvalues of this matrix A?
Root under -1, I guess.
Okay, so
Imaginary.
they are all imaginary, right? So assuming that you are only dealing with real vector spaces, so it's a technical point, but still assume that you are only allowed real eigenvalues, then does this matrix have any eigenvalues?
No, sir.
Okay, so this doesn't.
Sir, in the real world, we will deal only with the real spaces, right? We can't have imaginary things if we are working on the real problem, right?
I think value we can get imaginary.
So see, typically you will be working with, you will end up working with real eigenvalues, because so your data. So see, this will come up in various places, but you'll when you talk about a data matrix, right, you will eventually get some kind of symmetric matrix. Okay, so when you start looking at symmetric matrices, they have only real eigenvalues. So we'll come to that, right? It'll come up in week 5. So
Okay, sir.
week
Yeah.
5 is all about complex numbers. So there is a heavy use of complex numbers in week 5. We'll see.
Okay, sir. Yeah.
We'll see all that. So for now, there are no real eigenvalues. So I'll assume that there are no eigenvalues. And since eigenvalues and eigenvectors are inseparable, there are no eigenvectors. Okay, so there are no eigenvectors, right? Then the matrix is not diagonalizable. So specifically, this test you have, which is that if you have a matrix A which does not have n eigenvalues, okay, then you cannot diagonalize that matrix, because you will not get hold of n linearly independent eigenvectors. Okay, so note, don't worry too much about this. The n eigenvalues need not be distinct, and this is whatever statement I have here is only true for real vector spaces. But do you get this test? Whatever this test means. If you don't have n eigenvalues, then you don't have n eigenvectors, n linearly independent eigenvectors, and you cannot diagonalize a matrix, or rather the matrix is not diagonalized. Okay, moving on. So there is another test.
Sir, one doubt I have.
Yeah.
Sir, if you mean to say that if there are lambda square minus 1, so if the eigenvalues are not equal to 2, it's less than 2 means then it's not diagonalizable.
Okay, so lambda square minus 1, right? There are 2 eigenvalues. As I said.
No. For instance, I just said, like, if it's a square thing, then there should be 2 eigenvalues. If it is less than that, then it's not diagonalizable.
Yeah. Yeah, if it has fewer than n eigenvalues,
okay,
then see, the way to understand the negative test is, let's say the matrix, you assume to the contrary that it is diagonalizable. Okay, so a diagonalizable matrix will have n linearly independent eigenvectors, right?
Yes.
So it will have n linearly independent eigenvectors, and it will so okay, let me just show you why this is true.
No, I got the point, sir. I just wanted to this particular confirmation. That's what. If it's fewer than the actual polynomial, that power, then it's not diagonalizable.
Correct. Yeah. So
sure,
yeah,
sure.
But I also need to explain this part, because that is important. See,
yes.
Why this is the negative test comes from this property basically. So if a matrix A is diagonalizable, then it will surely have n eigenvalues, right? Because it has all the eigenvalues for corresponding to its diagonal counterpart, right? So if a matrix is diagonalizable, then it will surely have n eigenvalues. Now, if a matrix does not have n eigenvalues, then it means that you cannot diagonalize it. Okay, so that is where the property, that's where this negative test comes from.
Okay,
So,
sure. Thanks.
Yeah. Now the positive test, right? The positive test is as follows. You have, so consider two eigenpairs where the eigenvalues are not the same, they are distinct. So this is the question we are asking. Are V1 and V2 linearly independent?
Yes.
Okay, they are. So let's quickly see a proof for that. So assume that you have some linear combination of V1 and V2. Okay, so I'm just multiplying this equation by a minus lambda 1 I. Okay, so I just distribute this multiplication. You will get a minus lambda 1 I V1, a minus lambda I V2. Okay, so what do you think the next step will be?
A minus
A2 will be
What do you think is this first term?
this will vanish. The first term will vanish and will leave us with only one term.
Right? Why does the first term vanish?
Because it falls in the null space of a minus lambda 1 I.
Correct. Right. So V1 is an eigenvector of A, right? So V1 is an eigenvector of A with eigenvalue lambda 1. So A V1 equal to lambda 1 V1. That's what we have been doing all along, right? So this will become 0. You'll end up with just this. Okay, what is the next step from here?
Alpha 2 is equals to 0.
Okay, how do you get that?
Eigenvector, but it is not eigenvector corresponding to the eigenvalue lambda 1. So this part cannot be 0.
Okay, is there any intermediate step that I can try out here so that transition becomes clear? Okay, anyone else? Do you see what the next step should be?
Sir, yes, the first line, from the first line, we get to know that alpha 1 V1 is minus alpha 2 V2. So in place of that alpha 2 into a minus lambda 1 I into V2, alpha 2 V2, can't we put it as minus alpha 1 V1? No, it's not simple mathematics. It's like order also matters. No? Order.
We can just simply write it as alpha 2 into lambda 2 minus lambda 1 into V2.
Correct. Yeah, that is right. But can you break it down into a simpler step so that
Then alpha 2, lambda 1 is not equal to lambda 2.
Okay.
That's why we will have to take alpha 2 equals to 0.
all right? Okay. So see, since a lot of others, you are not. Are you following this part? Did everyone follow?
Sir, can we open the bracket, sir? Like if we go for alpha 2 times a times V2, and we know that a dot V2 is lambda 2 V2, and then again pulling out alpha 2 again common, V2 pulling out again common. So we'll have the other thing, we can put it in the bracket.
Okay, so that it is that step which I was looking for. So a times V2 is lambda 2 V2, right? I hope everyone is able to see that. Okay, so a times V2 is lambda 2 V2, and this is just lambda 1 V2.
Sir,
right?
what exactly are we trying to do here?
We are trying to prove that V1 and V2 are linearly independent.
Okay, sir. So we need non-zero coefficients. That's what. Right?
Exactly. Yeah. Okay. So next step. What?
As V2.
Okay,
so where is the first term, that is alpha 1 into a minus lambda 1 I into V1 gone?
that vanished here, right? Since v1 is in the null space of a minus lambda 1 I, this will become 0. Or a v1 is lambda 1 v1, right? So this will become 0.
Sir, how we wrote A as lambda to V2?
We didn't write a as lambda to v2, right? We wrote a v2 as lambda to v2. A times v2 as lambda to v2.
Okay.
Because it is given there that lambda to V2 is an eigenpair. So that means that A lambda to
we can write
A V2 is lambda to V2.
Yeah.
Okay, so after this step, what is the next step?
Sir, V2 is a non-negative vector. Lambda 2 and lambda 1 are different. So again, it will not be a 0. That implies that alpha 2 should be 0 there.
Okay.
Even alpha 1 we can say.
Right. So correct. So both are 0 because v2 is non-zero vector. Lambda 2 is not equal to lambda 1. Therefore, alpha 2 has to be 0. If alpha 2 is 0, then alpha 1 also has to be 0. So v1 and v2 are linearly independent. So did everyone get this?
Excuse me, sir.
Yeah. So is it which is this part clear?
Karthik sir, actually, this looks like a creative way of solving. But initially itself, if you can tell us like lambda 1, a minus lambda 1, like v1 is that is vanishing, like the equivalent things. If you can give a picture of it in the initial itself, we can understand. Like because in the course of the steps, we are not able to follow because the first part itself, if you can introduce what is equivalent to what, then that would be better.
Okay. Yeah. Right. Sure. So now it's okay, right? v1 and v2 are linearly independent. I hope you're able to see why.
Sir, hope you understood my query, no, sir. In the initial introduction itself, if you can give the equivalent things so that while we can follow during the course of the steps, we can get some picture as my.
You're saying that the entire thing you want displayed.
No, the last but third line, everybody are not able to understand. Like from how the transformation happens, like alpha 2 into a minus lambda 1 I into v2 equal to 0. The next step, how it becomes like alpha 2 into lambda 2 v2 minus lambda 1 v2 equal to 0. That step people are not understanding. So how is that? If you can give a picture in the starting only, that equivalence, so that we'll be able to follow it.
Okay. Right. Sure. I can make that change. Okay. So from this, what we get is this particular test, right? So if this is a generalization, we did this only for 2 eigenvectors. But if you have 2 distinct eigenvalues, then you have 2 linearly independent eigenvectors, right? And if you have n distinct eigenvalues, then you have n linearly independent eigenvectors. Okay, and if you have n linearly independent eigenvectors, then you have a diagonalizable matrix. Okay, that was a long argument. Did everyone get that part? This is the second test.
Will you just jot it down?
Okay.
Entire statement.
Okay, so see, this is the statement, right? So the what we just showed, what we just proved was that the step, let's say step 1, right? Step 1, what we proved was if a matrix has n distinct eigenvalues, then the corresponding eigenvectors are linearly independent. Okay, this is what we just showed. Namely, if there are 2 distinct eigenvalues, then the corresponding eigenvectors are linearly independent. Okay, I've just extended it to n distinct eigenvalues, then the n eigenvectors are linearly independent. Okay, that is what the first step is. The next step is if there are n linearly independent eigenvectors, then the matrix is Okay, this is the basic definition of a diagonalizable matrix, right? This is what we started off with. If you remember, if you have a basis of eigenvectors, then your matrix is diagonalizable.
So, so if I talk about this step 2 statement, so converse is also true. If the matrix is diagonalizable, then the eigenvectors will be linearly independent.
So yeah, if your matrix is diagonalizable, then you have a basis of eigenvectors. So they are linearly independent, right? So you can find. So I would put it this way: if a matrix is diagonalizable, you can find a basis of eigenvectors. Okay, all this seems too abstract, huh?
So is there a way to tell that the matrix is diagonalizable without knowing that the vectors are independent?
So you're asking if there is a...
No, I mean, you said that we can say that if the matrix is diagonalizable, then we have n linearly independent eigenvectors.
Right.
So, but don't we know that the matrix is diagonalizable because we know that the eigenvectors are there are n linearly independent eigenvectors. So is there a different way to tell it is diagonalizable is what I'm asking.
The other definition, right? So if a matrix is similar to a diagonal matrix, then it is diagonalizable. So these are the two ways.
Okay, yeah, that makes sense. Thank you.
Sir, here I want to ask one thing. That
yeah.
They are n linearly independent eigenvectors. Then by using Gaussian elimination technique, we can find the basis for these vectors, eigenvectors.
The eigenvectors themselves form a basis, right? Because
okay.
They are
fine standard basis.
Right. See the n eigenvectors are linear. If the moment I say that there are n linearly independent eigenvectors, then they form a basis, right? So see, basically for a matrix to be diagonalizable, you must have a basis of eigenvectors. That's the main, it's the underlying point here. Okay, so any questions in this positive test? So there are two tests that we have seen. Negative test is mainly with respect to the number of eigenvalues that you have. If you don't have n of them, then you can't diagonalize the matrix. This positive test is if you have n distinct values, eigenvalues, then you can diagonalize the matrix. Okay, so there is, between these two, there is one more question which you can ask, right? So what if a matrix has n eigenvalues, but some of them repeat? So do you all see where this question comes from? Or is it too confusing at this stage?
Sir, that means that there are no n distinct eigen.
Yeah, good point, right? It's the question is coming from that. So the question is coming from this positive test. So positive test says that there are n distinct eigenvalues, then we are set. Okay. So what if there are not these n distinct eigenvalues, right? Then from the negative test, what do we know? If we don't have n eigenvalues, then it is not diagonalizable. But there is this third case, right? That there are n eigenvalues, but some of them repeat. So this is the third test. The third case. Okay, so
when the eigenvalue is repeated, then the positive test will fail, right?
No, right? So see, we look
they
at
are
these.
Not linearly independent.
One second, right? So I'll just list down the three cases, right? So case one is you have n eigenvalues. You have n of them, right? Not necessarily distinct. Okay, so rather this will be case 3. You have n distinct eigenvalues, right? You have n of them and they're all different from each other. Case 1 is don't have n eigenvalues, right? Including repetitions, right? I include repetitions here. Okay, so this is the positive test that we are talking about, right? Sorry, negative test. If you don't have any eigenvalues, then there is no hope, right? The matrix cannot be diagonalized. If you have n eigenvalues, then the matrix, it's a positive test, right? I am positively saying that you can diagonalize the matrix if there are n distinct eigenvalues. Now, the third case is you have n of them, but they are not distinct, so you can't enter into case 2, right? You this is also not the same as case 1, right? Where you don't have an eigenvalue, you have an eigenvalues, but unfortunately they repeat. Okay, so n eigenvalues, but they repeat. Sorry, same step. They certainly do repeat. So this is the no man's land that we fall under. Is this clear? The three cases.
No, I'm saying, sir, if there is some repetition in eigenvalues, still, can I say they are independent, all are?
No, that is what we are coming to, right? If see, there are two things, right? There is
No,
count.
I just failed to understand why you are making case 3 when the case 3 statement itself is a failure case of case 2.
See, okay, so I get your point. So you're saying that, see, there are, if there are n distinct eigenvalues, then it is diagonalizable. Okay, that is the statement.
So either claim 2 and case 2 is wrong, So if you are claiming like if we have n distinct eigenvalue, then only it is positive case. So either we have to make this case flexible.
Sorry, I didn't get the point.
So what sir is saying that case 2 is one possible way to get a positive test. For case
Exactly.
3, it's not sure.
Exactly, right? So okay, so it's not like I didn't say that you need to have n distinct eigenvalues for a matrix to be diagonalizable, right? This is if then, right? If then, you have to understand this. It's like an if block, right? If you have n distinct eigenvalues, then the matrix is diagonalizable. Now, if the matrix is diagonalizable, then does it mean that it should have n distinct eigenvalues? No, right? So for example, you take an identity matrix. So you take I equal to 1 0 0 1. Okay, so this has only one this has two eigenvalues, right? But they are not distinct, but it is still diagonalizable because it itself is diagonal. All diagonal matrices are, by definition, diagonalizable. Okay, so now, are you saying that this doesn't fall under case 2? Is that your confusion?
This case is case 3, that what you are.
Exactly. This is case 3, right? In this case, you have two eigenvalues, 1 and 1, but they repeat. Okay, so this falls under case 3.
Can we say that even if there are repeated eigenvalues, but since eigenvalues are just scalings of the of the column vectors or the standard vector, so even if they're repeated eigenvalues, it can mean that two of the column vectors have got the same scalings. That could mean that way, right?
No, I'm not sure about that argument. But we'll come to that, right? So we'll come to that. I first want to eliminate this confusion around these three cases. Is it still confusing why we have these three cases?
No, not. It's okay, but the only thing is that even though we have a repeated many eigenvalues in repetition, but still we can able to have the different eigenvectors.
Correct. That is why this third case is a no man's land. It's like inconclusive test. You cannot conclude anything if you have any eigenvalues. If you want to really conclude something, then they must either be distinct or you must not have all n of them, right? Like the lambda square plus 1 case, right? Lambda square plus 1 equal to 0, no eigenvalues. So you can straight away rule out diagonalizability. Or if you have n distinct values, then you can positively say that it is diagonalizable. We come to this case, right? I'll take an example here. Here example helps.
Sir, I have one question here.
Yeah.
Can we do it like this way that suppose if out of n there are m repeating lambda values, so n minus m are distinct, and somehow with some mathematical manipulations we try to see that these m similar values where they lead to, and on the basis of that if we can arrive at whether the matrix is diagonalizable or not.
That is a bit tricky, right? So that's a bit tricky. So we'll see this example, and you'll find out, right? So we just stick with me for this example.
And let's say like we start with case 3 because it is inconclusive. So how to tackle it to conclude?
It's tough, right? So that requires extra mathematics. So in this, that is beyond the scope of this course. That is a very usual common dialogue that we employ when we don't know what to say. So I will also use that dialogue and say that is really beyond the scope of the current MLF course. So for now, we'll just state that it's inconclusive. I think there are, if you take up a proper advanced linear algebra course, you will study what to do in such cases, right? So there are these ideas of multiplicity of eigenvalues and all that, right? So I don't think we want to go there now. Okay, so let me just finish this particular example. What happens if you have two eigenvalues here, but they are the same, right? Lambda equal to 2 is the only eigenvalue. So in such cases, what you do is you look at the eigenvectors, right? A minus 2i times v equal to 0, right? You are actually solving for the eigenvectors. So if you solve for the eigenvectors, then you see that every eigenvector is of this form k times 1 comma 0, right? So you are only able to get one linearly independent eigenvector, right? You are not able to get two linearly independent eigenvectors. Okay, so this particular matrix A is not diagonalizable.
Will you repeat the entire thing again?
So 2 is the only eigenvalue, right? That is clear. Because 2 is repeated twice. There are two eigenvalues, but 2 is the only eigenvalue. I mean, it has only lambda equal to 2 is there. So you go ahead and find the eigenvectors. So a minus 2i times v equal to 0. So we are finding the eigenvectors. So you get this equation v2 equal to 0, which means v1 can be anything, right? V1 can be anything. So you're characterizing all possible eigenvectors corresponding to lambda equal to 2 as span of 1 comma 0. Okay, every possible eigenvector is of this form. For this matrix A, there is only one eigenvalue, and every eigenvector corresponding to this eigenvalue will be in this set.
Yes.
Okay, now since this subspace, right? This subspace has only dimension 1, right? It is just span of some vector. I cannot pick up two linearly independent eigenvectors. And from my definition of diagonalizability, if I am not able to find a basis of eigenvectors, I cannot diagonalize that matrix.
Oh, from case 1, it is failing.
So
no, it is case 3, but finally, because of I am not able to span the whole.
You basically go back to the definition of what a diagonalizable matrix is, right? You cannot span. You're right. So you cannot span Rn using eigenvectors.
Sir, in the end of case 2, we came across the equation that alpha 2 into lambda 2 minus lambda 1 v2 equal to 0. So can we use this to say that in case we have lambda 2 equal to lambda 1, we can't exactly be sure whether alpha 2 is 0 or not, and that is why we are in that no man's land.
Right. So yeah, you're saying here, right? So
yeah.
Okay, so that's a good point. So let's start. If we start from here, assuming that this is equal, then we can, if we go through all these steps, we will end up here, right?
Yes, precisely
Yeah.
there. So since we don't know if alpha 2 is 0 or not, in the previous case, since we know that lambda 2 and lambda 1 are distinct, we can say that alpha 2 has to be the one that is 0. But in this case, we cannot say the same.
True, right. So I don't know if this is...
This seems more convincing. Yeah.
Right. You are right. So I don't know if this is rock solid proof, but this is a very good approach. I mean, this is a good approach to understand that V1 and V2 need not be linearly independent if you have equal eigenvalues. So that might explain my inability to find two linearly independent eigenvectors. Yeah, I think that's a good argument.
So why can't we say the third case as a solid proof? If there is no n distinct eigenvalues, it's not diagonalizable. Why are we saying that we can't conclude?
So this is the case, right? So the third case is, this is the third case, right? You have n eigenvalues. Here you have two eigenvalues, but they are repeated, no? So if they are repeated, in this case, I cannot find two.
So it will be the same for every case, right? It is not spanning. So we can say, right, it is not diagonalizable.
So in case 2, you can find, right? Because if you have n distinct eigenvalues, then I have this property which says that eigenvectors corresponding to distinct eigenvalues are linearly independent.
Yeah.
So I'll always be able to find n linearly independent eigenvectors in the second case. Right? So maybe I didn't understand the question properly.
So may I answer the question?
Yeah.
Understand the question that ma'am is asking.
Yeah, please.
I think she is saying that in case 3, like the example you gave, it clearly concluded that if there are repeated eigenvalues, we cannot find two linearly independent eigenvectors. So why don't we take this as a conclusion? Why we are saying this is a no man's land. So I am saying in the same matrix that sir gave as an example, if we replace the 1, 2, 2, 1, 0, 2, instead of that we take 2, 2, 0, 0, 2, meaning the diagonal matrix, then we can find two linearly independent eigenvectors corresponding to 2. So that's why sir is saying that it's no man's land. In both cases, we have two. In both the cases, we have two.
It depends on the matrix, right?
Yeah, exactly. Depending on the matrix. That's why.
Right.
Okay. Can I, sir, if we take a 3x3 matrix just to differentiate,
okay.
Suppose we have 3 pairs of lambda 1 v1, lambda 2 v2, lambda 3 v3.
Okay.
There are 3 pairs, right? Eigenvalue and an eigenvector. When you say distinct, you mean to say the set of all eigenvalues corresponding to the eigenvector needs to be different or same. That is what you're trying to imply. Is that what you're trying to imply?
So I'm saying that lambda 1, lambda 2, and lambda 3 should be pairwise distinct. So none of them should be equal to each other.
Yes, Mother, when you're saying distinct, it is you're comparing pairwise, not that like lambda minus, in this case, lambda equal to 2, you written is the only eigenvalue of A. So when you're saying it should be distinct, it is the pairwise distinct. That is what you're implying, right?
Pairwise distinct, but that would result in none of the eigenvalues being identical, right? So for example, if you have a matrix,
can you write set of 2 2s and make sure what happens? Let us take a 3x3 matrix and write a pair of 2 eigenvalue eigenvectors and see what's happening.
So I might have to get hold of a proper example, but see,
let's not worry about the linear independent part. Let's only worry about the eigenvalue and some vector. We can say v1 or something, and maybe we can use it.
Okay, so I don't know if this particular matrix is diagonalizable or not. Okay, but I think that this has three eigenvalues, right? 1, 2, and 2. Okay, typically if you take up some kind of upper triangular matrix where the or lower triangular matrix, right, where below the diagonal and above the diagonal the values are 0, then you can read off the eigenvalues as the diagonal element. So assuming that that is true, A has 1, 2, and 2. It has three eigenvalues, but some of them repeat. Now in this case, it's very tough for us to conclude without actually going into the eigenvector computation if it is diagonalizable or not.
Can you just write the corresponding eigenvectors?
That will be tough, right? I would have to solve for it. So I would have to solve for A times A minus lambda I times V1 equal to 0. Right? We can try to do that, but I don't know if we will end up there. So I would have to solve for, say, assuming that
let us assume there are three eigenvectors. Okay, we'll not calculate if it is taking time. But 1 is an eigenvalue, 2 is an eigenvalue, 3 is an 1, 2, and 2 are eigenvalues, right?
Right.
So correspondingly, there are three different vectors.
Not necessary is what I'm saying, right? So you don't know. So it depends.
We are assuming the case there are three different vectors. Suppose let us take the case where there are three different vectors and then go other ways.
Okay, if there are three different, I mean, if there are three linearly independent eigenvectors, then you can diagonalize the matrix. That is the claim.
Even though the eigenvalues are repeating, if the eigenvectors are linearly independent, then we can diagonalize it.
Exactly, right? Yeah. So that is the extreme case is the identity matrix, right? So you have, so the extreme case is the identity matrix where you have only one three eigenvalues, all three are one, but you have what?
Can we go back the slide once again? What? No, not slide. Whatever happened before, where we were 1, 2, 2, and the maybe
okay.
1, 2, 2. There was something on the right side. V1, V2, V3. Yes.
Yeah.
That was on V1, V2, V3. Just to clarify, if V1 out of now we are very clear with this example. 2 and 2 are equal and the equal eigenvalues. With V1, V2, V3, we just want to say that all three are distinct. Then we'll have a eigen space or something. Other it is diagonalizable. Okay. But
yeah,
if only two of them are there, then we can't say it is diagonalizable. That is why we cannot say with surety what is happening. Is that what the entire summary is?
Yeah, entire summary is that if you have repeated eigenvalues, and see this V1, V2, V3 is like components, right? They are components of one vector. So we can't do much with those components alone, right? I was more talking about three separate vectors V1, V2, V3, right? So V1 should correspond to, say, an eigenvalue of 1. V2 and V3 maybe correspond to eigenvectors of lambda equal to 2. And these three together should be linearly independent. Is that convincing or?
So the only difference for the identity matrix, in case of identity matrix, we can see this thing in another way. Like there is a 3 vector. An identity matrix means the linear transformation on that corresponding matrix actually is not taking to anywhere. It is staying in the same class. So all the 3 remains 3 and span the whole space.
Correct.
But whenever there is a linear transformation is happening, we don't know where this vector goes. We have to check.
True. Yeah. So see, it is, I mean, I understand it can be confusing. So for example,
but in a few cases, like in this case, we are sure, right? The y-axis and the z-axis have been scaled by 2 and the x-axis remains the same. Like if I say their axis, right? the two of they have been scaled. So here we know that the previous property has been preserved. So you can kind of diagonalize it. It remains independent. So
maybe, may not be, because you are fixing one axis and you are enlarging another two. Now the point in this 3-dimensional space by fixing one axis and stretching other two will take you some other place. Take you.
But the bases remain independent still.
Yeah, see this matrix. Are you talking about this matrix being diagonalizable or not? This is already diagonalizable, right? By default. All diagonal matrices are diagonalizable, right? You see, you must switch back and forth between these two properties, right? This, you're asking if this is similar to some diagonal matrix, right? This is, so can I write this? Can I write A as some QD Q inverse, right? No, it's just purely algebraic perspective. You can write Q is just the identity matrix here, right?
Yes, so this is already
right. So this is already diagonalized. So all diagonal matrices are diagonalizable. Okay, so remember that what is the point of looking for diagonal matrices? To see if they are somehow closely related to diagonal matrices, and if it's already diagonal, then we don't have to worry about anything.
Because a diagonal matrix is always from the basis of that space.
Yeah. If you have a diagonal matrix, then your eigenvectors are already, they form a basis for Rn. So that way also you can look at it. Okay, so yeah, so this can be confusing. Please go over this again. It's not necessary that you have to understand this right away. It will take time. This is a very tricky topic. So I don't expect all of us to immediately grasp the whole thing. Okay, so we'll if it's fine with you all, we'll move on to.
Yes, a Fibonacci to understand.
Yeah, I hear Nitin's voice. Is anyone watching MLT live session by any chance? Okay, so we finished till this part. So finally, we'll see one example. Maybe it might make certain things clear. Okay, so what is an application of diagonalization? Let's see. Okay, so this is familiar ground for most of you. At least this sequence you have seen enough number of times. You would have seen it in Python for recursion, and in elsewhere also you would have seen it. So the question that we are asking is this, right? What is the kth term of the sequence? So using Python, of course, we can, any programming language, we can compute the kth term, right? Programmatically, we can do that. Computationally, we can do that. But is there a mathematical formula that we can find out, right? Where you plug in the value of k and then you get fk, right? For example, so the sum of the first k natural numbers is, you have a formula for that, right? K into k plus 1 by 2. I just plug in k and then I get the kth term of the sequence, right? So is there something like that we can do for the Fibonacci series sequence, right? So that's the question, and we'll try to answer this using diagonalization, and you'll see how it kind of turns up in the most unexpected place. So we'll start with fk plus 2 in general. So what is the formula for, or what is the relationship between fk plus 2 and other terms of the sequence?
Fk plus 1.
Okay, so that is the relationship. So what I'm going to do is, I'm just going to add this extra equation, which is nonsensical. I mean, it's like redundant, but still I'm going to add it. I'm going to rewrite the two sets of equation in this way. Is it clear so far?
Yes, sir.
Okay, so now what emerges out of this? What do you see coming out of this?
A
Vector
system of
matrix
linear
multiplication.
Right. So it is matrix vector multiplication. This just becomes 1 1 1 0 fk plus 1 fk. You just go back quickly. So 1 1 1 0 goes into a matrix. Fk plus 1 and fk go into one vector, and on the left hand side we have fk plus 2 and fk plus 1.
Sir,
Okay.
just one question, sir.
Yeah.
Proceeding further, sir. So how you have this intuition key? I am forming this thing. See, for a Fibonacci series, like the first summation of the first n term, as you explained, k into k plus 1 by 2. But from looking the Fibonacci series, from where you got this intuition, I will form this as a matrix vector multiplication.
So all credit goes to Mr. Gilbert Strang. So I mean, you must ask. You must ask how. So if you ask him, he will credit his teacher and so on until I don't know where it stops. Right. See, these are some great mathematicians have done it, and most of it is like pattern matching, right? So I really don't know. So we'll have to dig into the history of the subject. So that might have some explanation, but it's a good question. See, if you are able to figure out the answer for this question, then I'm also interested actually. I want to know how problem solving really works, right? I mean, leave exercises. Whatever we have in our assignments are all exercises, right? You already know how, you know the formula, you just apply it, you get answer. But if you are given a new problem, from where do you get these insights, right? So it's a big insight, right? And you will see, I mean, if you have not seen this particular piece of math, then it's just mind-blowing actually. I mean, how they came up with this linking something like, see, Fibonacci is all about integers, right?
Yes,
and so if you jump to the last slide, you will see all kinds of crazy expressions come up.
And I think it's a kind of synthesis,
Yeah, true. Yeah, I honestly don't know from where they get hold of all these things, but
I think, sir, it is somewhat of a god gift because not everybody can just by looking at the numbers visualize and form patterns. I mean,
True.
Just look at the movie of Ramanujam. You see, the doctor comes in and he says that I came by a taxi which is having this number, and he said that this number is not something very common, but it is the sum of some squares and cubes. So he had that ability to by just looking at the number, visualizing it, and forming the patterns. I think that is something one in billions and maybe God gift.
Yeah. So yes, let's see, right? So yeah, coming back to MLF. So what we have is this matrix form, right? It's a cute expression, and so what do we do with this? We push it to the left hand side and we introduce variables because that will make our life easier. We call this matrix A. This vector is UK, right? So if this vector is UK, then this is UK plus 1. I hope you all see this, right? So this is just the next set of terms. So I end up with this kind of a relationship where UK plus 1 is A times UK. Matrix vector, here is a vector. Okay, this step I hope is clear to everyone. Okay, so this is what is called a recurrence relation, right? So and we can see the term recurrence very closely ties back to recursion, right? So the k plus 1th step depends on the kth step, and if you recurse, you can go back to your base step, right? Your base case. So if you want to get the next step, then you multiply UK, the current step, by a matrix A. That's what this means. So the first step or the base case will be 0 and 1, right? So those are the first two terms of the sequence. The next term is just A times U0. So U2 is what? A times U1. And it's nothing but A square times U0, right? I just keep substituting things here. So U2 is A square U0. So how do I generalize from here?
I think we can say UN is equals to A to the power n U0.
Right.
Maybe.
Okay. So that is what I'm going to do. I'm just going to use UK. UK is going to be a power k times u0, u0. So is this equation clear to everyone?
Yes.
Yes, sir.
Yeah. So if you're clear till this, right? Now this is where diagonalization enters, right? You need to find the kth power of a matrix A, and remember what we started off with, right? For diagonal matrices, computing the kth power is very easy. Okay. And we also saw that if your matrix is diagonalizable, then in that case also computing the kth power is easy. So our hope is that if we can show that A is diagonalizable, then we can compute this expression very easily. Okay, so that is what we'll do next. How do we compute A power k? We'll try to see if A is diagonalizable. Okay, so is A diagonalizable? And this is what we'll be doing next. So what is the first step that we should do if you want to find
the eigenvalues?
Exactly. So we find the eigenvalues. So remember the matrix, I won't be displaying the matrix from now on. It's 1, 1, 1, 0, right? So it's 1 minus lambda, 1, 1 minus lambda. I set this determinant to 0. So I get this 1 minus lambda minus 1 is 0. So I get this lambda square minus lambda minus 1 is 0. Simple quadratic equation. I get two roots, right? So lambda 1 is 1 minus root 5 by 2. Lambda 2 is 1 plus root 5 by 2. I have two eigenvalues. So now what can you say about the eigenvectors?
Distinct eigenvectors.
They are linearly independent.
Exactly, right? So you have two distinct eigenvalues, and therefore from case 2, right, or from the positive test, you can now conclude that the matrix A will have two linearly independent eigenvectors. So that is what we'll do next. We'll compute them. So to compute them, assume that I take one of these two lambdas. I just call it lambda. So A minus lambda I times V is 0. Okay, this is A minus lambda I. This is V 0. If you solve this, you will get this equation, right? You just take the second equation, V1 minus lambda V2 equal to 0. So V1 by V2 equal to lambda.
Yes, sir. Yes.
Okay, so do you all agree that these are two eigenvectors? This is, I have skipped some steps, but is this clear why this is true?
Yes, yes.
Okay, see what we are doing is we are setting V2 equal to 1. V2 equal to 1, then V1 becomes lambda 1, right? So
yeah.
So lambda 1 comma 1, lambda 2 comma 1 are two eigenvectors corresponding to the two eigenvalues, lambda 1 and lambda 2. So are they linearly independent?
Yes, sir.
They are, right? Because you cannot express this as a multiple of the other.
Yes, sir.
Okay, so we have two linearly independent eigenvectors. Therefore, what can you conclude?
Diagonalizable.
A is diagonalizable.
It is diagonalizable.
Exactly, right? So A is diagonalizable. So that's what we have, right? So A is this matrix Q, right? Remember Q, the matrix Q is nothing but the set of eigenvectors, right? So lambda 1 comma 1 is the first column of the matrix Q. Lambda 2 comma 1 is the other column of the matrix Q. D is the matrix of eigenvalues on the diagonals. So I can write A as Q D Q inverse. Okay, so I hope this is clear. Okay, so far so good. So we need to compute this Q inverse that you can do by Gaussian elimination. Okay, so it comes out to be this expression. This is something you all know. Even otherwise, don't worry too much. It's like quite easy to compute Q inverse. So this is the setup, right? Once we have come so far, we'll go back to the formula, right? Or rather, we'll go back to the Fibonacci sequence, the recurrence relation. The kth term is A power k times U0, right? And U0. So we now know what A is, right? Q D Q inverse. So I'm just going to substitute that. Okay, so what will be the next step here on the RHS?
QD to the power k, Q inverse U0, I think.
Okay, so that is so this is the place where diagonalization has helped us a lot, right? See, the whole point of the doing diagonalization is this step, right? If A were not to be diagonalizable, we couldn't have done this step. Okay, so this is where we are. So we know all the quantities on the RHS, right? We know Q, we know D, we know Q inverse, we also know U0, U0. We are just going to substitute them, right? So this is Q, lambda 1, 1, lambda 2, 1. This is D power K, lambda 1 power K, lambda 2 power K. This is Q inverse. So I've just taken the constant here outside. So this part is Q inverse, and this final part is U0, 1 comma 0. Okay, so if you multiply the whole thing together, this is just plain matrix multiplication.
Yes, sir.
You end up with this expression. Okay, you end up with this expression for UK. So can you now tell me what FK will be? Compare these two. UK is, what is UK? UK is nothing but FK plus 1 comma FK. And after all your computation, you have ended up with this particular expression on the RHS. So what should FK be?
Lambda 1 per K minus lambda 2 per K by lambda 1 minus lambda.
Exactly, right? That is FK. That is FK. That's good. So now let's go back. Like, what are lambda 1 and lambda 2? They are these two values, right? 1 minus root 5 by 2, 1 plus root 5 by 2. Now we just substitute it. So what will be lambda 1 minus lambda 2?
1 upon root 5.
1 by 2, right?
So, no, 1 upon root 5, I guess. Yeah.
1 minus lambda 2 will be
Minus.
minus root 5.
Yeah, it is minus root 5, right? So it is minus root 5. So so if you just flip the signs, right, you will get 1 by root 5 times lambda 2 power K minus lambda 1 power K, right? You just don't want the minus sign. So you finally end up with Fk is equal to 1 by root 5 times this crazy expression. Okay, so that is the kth term of the Fibonacci sequence. And the brilliant fact is that it's an integer, right? So the left hand side is an integer, so obviously the right hand side is also an integer. But look at the number of radicals, the surds that are here, right? Root 5 is all over the place.
So is it yield the actual value or approximate value?
No, this is the actual value, right? Because we have not used any approximations anywhere.
Yeah. It's brilliant.
Right? Yeah. So this is actually brilliant. So this is somehow it all works, right? So diagonalization is worth learning for at least computing this formula, if not for MLF.
Machine learning.
Yeah.
Correct.
Yeah.
That's
anyway,
so
but
interesting.
Right.
So in this sense, the expression inside the denominator, both of them will end up having 2 to the power k. So in the numerator, I think we'll always end up with something that also has root 5 in it, because the root 5 outside also has to get cancelled again, right?
Right. It should have a root 5 there. Yeah.
So the term that is along with root 5 will probably be giving us the answer.
Right.
So in case like, let's say like K is very large, then in that case, can we take approximation?
Yeah. So
Right hand part becomes 0.
Right. Yeah. So that part I have skipped. So I haven't. So 1 minus root 5 by 2. What is the value of 1 minus root 5 by 2? It's fraction, some kind of a fraction, right?
Yes.
Yeah. I don't know exactly what it is. So maybe we can quickly compute that. See, ideally MLF should have some programming also, but anyway. I would suggest that all of you learn NumPy as soon as possible, because in MLT you'll be doing a lot of NumPy, and let us try to compute this part. 1 minus root 5, right? 1 minus root 5. Yeah, so 1 minus root 5 by 2 is like this value, and if we raise it to say some power like 100, this becomes vanishingly small, right? So that second part, this 1 minus root 5 by 2 power k will vanish as k tends to infinity, and you can say approximately fk is 1 by root 5 into 1 plus root 5 by 2 power k for very large k. And good point. Yeah, that's a good point.
We are considering 0 as the first term, right? Like we are taking it as that will be f0 or f1.
U0 you mean, right? F0 has 0. So F0 will be 0, F1 is 1.
And in the case of approximation, right side will be some fractional value, but left side will be like integer, right? So it will be contradictory.
It won't be. I won't say it is contradicting because we are already approximating, right? So, I mean, we'll try. I mean, we can try. We still have some time, so we can try the whole thing. So this is what I'll just 1 plus root 5 by 2, right? So let's call. I'll call this left. Left is 1 plus root 5 by 2. Right is 1 minus root 5 by 2, right? So 1 plus root 5 by 2, 1 minus root 5 by 2. And the kth term will be what? 1 divided by root 5. So this is the multiplier outside. This multiplier into left power k minus right power k, right? So this is the kth term. We can just return this particular value. Okay, let's just do some Python for a while. So let's try to print the first 10 Fibonacci numbers and see if this formula actually works or not. Okay, so this is some floating point error, so that can be ignored, right? So you are not going to get exact integer values using Python. So what we can do is we can just typecast this to an integer or round it off.
But seems okay even with floating point.
Right. 0, 1, 1, 2, 3, 5, 8, 13, right? So this is quite good. So what would be interesting is,
can you remove the right part and then try? I mean, just since we're talking about approximation then. So if we round off after removing the right part, I think we should more or less get this.
Yeah, you can take ceiling function.
Right. So you want me to remove the right part, right? So let's see how good, as an approximation, we want to study this, right? So how good of an approximation is this? Okay, let's. Not bad, right? Even for
only higher values, right? Not
so if we round it off, I think we will get the exact values actually.
Yeah, no, even for the small values, this seems to be pretty good, right? So
yeah,
if you look at this, this is 0, 0, that's fine. 1, 1, 2, 3, 5, 8.
No, 2 is missing.
2 is missing.
5 is missing. Yeah, it's not coming.
So we could do one thing. We could return both, right? We could return the approximation and the actual thing. So the actual thing is this, right? You return both. Return both.
No, this is the approximation, right? You have dropped the right term.
Correct. Sorry. Are we missing something?
Bracket.
Okay. So approx actual, right? 0, 0. No, something else is not right. Okay, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. We'll try for.
Sir, can you remove the 8 there? I think it is rounding off 1.7 as 1 in the fourth one. So if we go for how we normally round up like greater than 1.5 as 2, then I think we should be getting 2. So.
Okay, I don't know if round will work. Let's see.
Yeah, right.
0, 1, 1, 2. Wow, this is.
Yeah, the thing is previously it was rounding off 1.7 as 1. So since we made it to be 2, since it is closer to 2, I thought taking it on.
Okay, so this approximation itself is good enough, is it? That's what it seems, right? Seems like. So if you run this for, say, so does it mean that, so can I say, if I write this particular function, let's just, I'm not returning anything, I'm just making sure that this, okay, so this approximation is then good enough for all values of k then, right?
Yeah, so if the first few values since it satisfies, then the k only goes on decreasing, right? The right so
right.
It has to go.
True. Yeah, that's good. So this is a very powerful formula then in that case. You can just throw away this part and then say that round off this 1 by root 5 times this will give you the kth term of the Fibonacci sequence.
So, sorry to again deviate. So do you know if like who gave this at what year? I mean, you mentioned Hilbert's time, so it should have been relatively recent.
Which one? This formula you are saying?
Yeah.
This formula. See,
first published by Hilbert's time, then this should be a relatively recent.
I am not sure. See, eigenvectors, eigenvalues have been around for a while, right? So, I am not sure, but I'll do some digging and see if I can find out if Strang has referenced this particular material somewhere, then that might give us some idea how old this particular formula is.
Yeah, because this seems like a really good thing to have been, like, if it was just like found by starting the Fibonacci, it seems like a really good thing that was.
Right. Okay, so I have just one more part, and with that we'll close, which is the last part of week 4 really, which is orthogonally diagonalizable matrices. Okay, so that's like too many terms. So let's very quickly look at this. So orthogonality, I think you all remember orthogonal or orthogonality. So if you have n vectors v1 to vn, so if the dot product is 0 for their pairwise orthogonal, and if vi transpose vi equal to 1, then you have a set of orthonormal vectors. This you all remember, right, from Max 2?
Yes.
Okay. Then what can I say about this beta, this set beta? It is what for Rn?
Basis.
Yeah, it is a basis for Rn, right? It is interesting thing is that it's not just any basis, it's a basis of orthonormal vectors. I hope you all remember this.
Yeah.
Right? Okay. So this is beta. Now let's put all these vectors into a matrix Q. Okay. So now what is Q transpose Q equal to?
Should be 0, right?
Not to, everything need not be 0, but it's quite right. I mean, there will be a lot of zeros. But
Where it's orthogonal, there will be 0.
Identity.
okay, right? It will be identity actually, right? Because
Diagonal is 1.
Yeah, all the diagonals will be 1 because diagonals will be Vi transpose Va. Okay, V1 transpose V1 will be 1, V2 transpose V2 will be 1, so on. But everything else will be 0. So Q transpose Q is I.
Identity matrix.
Yeah, right. So these are what? These are called orthogonal matrices where Q transpose Q equal to I. So Q inverse therefore is nothing but Q transpose, right? This is from the basic definition of invertibility, right? So if A be equal to I, then B equal to A inverse, all that, right? So this is what we have here. These are orthogonal matrices. So why are orthogonal matrices interesting?
Mainly for projections, is that correct?
From a more computational standpoint, can you see why they should be studied?
They are multiplied and give us an identity.
Okay. So I'll just put it a slightly different way.
Help us find inverse there.
Right. You just need inverses. Correct. You just need to take the transpose to find the inverse, right? You don't need to do any Gaussian elimination, all that heavy duty stuff, right? You just take the transpose and you're done. Okay. So the whole point of orthogonally diagonalizable matrices is that if you can find a Q which is orthogonal, then you can write A as QD Q transpose.
And the inverse is now the transpose.
Yeah, right. So this is, see, there are some matrices which are not diagonalizable. There is a small set of matrices which are diagonalizable, and in that subset, you have another smaller set, right, of orthogonally diagonalizable matrices where you can diagonalize it with an orthogonal matrix. So that is this class. Okay, A equal to QD Q transpose. Now, what can you say about A transpose?
Equals to A.
A transpose equal to A, which means A is symmetric, right? So if a matrix is orthogonally diagonalizable, it is symmetric. That is what we have arrived at. So interesting question is, if a matrix is symmetric, is it orthogonally diagonalizable? Okay, this is a question.
One point. How did we arrive at A transpose equal to A?
So you have QD Q transpose, right? You have QD Q transpose. Now, if you take A transpose, then this is the whole transpose, right? This is nothing but you reverse the order and then you take the transpose, right? So it's Q transpose, the whole transpose, D transpose, Q transpose, correct? I just reverse the order and then I take the transpose, right? AB transpose is B transpose, A transpose. So this D is diagonal, so D transpose is D. So okay, so that is how we arrive at this part. Now you can now take the converse of the statement and ask if it is true. So if a matrix is symmetric, is it also orthogonally diagonalizable? The answer is yes, and that's what week 5 will be all about. So week 5 will take a detour. We will study complex matrices, right? And try to show that symmetric matrices are orthogonally diagonalizable. Now all this is required for one concept called SVD or PCA, right? So if you look at this popular ML package, right? So this is some kind of a dimensionality reduction. If you remember dimensionality reduction, so we studied it in week 1, right? Or Professor Harish was mentioning that it's a good idea to reduce the dimension of your data matrix, right? So PCA is one such method. Okay, PCA uses this thing called singular value decomposition, for which you need to study eigenvalues, eigenvectors, symmetric matrices, the whole thing, right? So you can you see where this is going, right? You all this is required for you to study this PCA. That's where we are going. Okay, so that's all I had. We are done with week 5 in general. If you have any questions, we can take them up, or if not, we'll close the session.
Yes, sir. So it's just one small question.
Yeah.
In the beginning of the lecture for week 4, the lecture
Okay.
started with forming differential equations and then providing a solution of the kind ut is equal to e power at times u naught. And then it was stated in the lecture that the solution is obtained via, if the solution is there, then we have a matrix A. And then the entire week started with eigenvalues and eigenvectors for all this. So I just want to ask that whether this eigenvalue vectors is limited to only cases where we have differential equation form of system of equations and we want to find a solution for it in the form of eigenvalue or eigenvector, or it is applicable to other things like you stated that for any linear transformation from V to V, then we associated the associated matrix X. So I want to know that this eigenvector is specifically for a system of linear equations in the form of differential equations.
No. So good point. See, Gilbert's triangle uses one way to motivate eigenvectors, right? And see the basic reference book is Gilbert's triangle, right? If you look at the lectures, they are modeled based on that. So Strang is like a textbook for engineering, right? It's an engineering and it's like an applied linear algebra kind of a textbook. So differential equations come up very commonly in, say, mechanical engineering and electrical engineering and many other engineering disciplines. So the audience, is very well suited to understand, or they may come from that kind of a perspective, right? For us, maybe it's not the best introduction. So, but you must not go away thinking that it is only arising from differential equation. That's not true, right? There are many other places.
Because the lecture started with the that regression, and then in RD space, and then it took out differential equations, and then he said, then the lecture states that now if you want to solve it, then you need to arrive on the value of eigenvalues and vectors. So I thought that specifically if it is meant for this thing.
No.
But it is not applicable for. Okay.
It is applicable in wide variety. So, for example, so you can look at PageRank. So Google's PageRank, Google's algorithm for ranking web pages, right? It uses this algorithm called PageRank, and if you look at it, PageRank tries to solve an eigenvalue problem. So I don't know if Wikipedia has the search for. Okay, so I'm just telling you that this is not some random concept that we are studying, and eigenvector is very much part of data science. So okay, I don't know where it exactly comes up, but I hope you can see that it's there, right? So PageRank is a typical ML algorithm, you can say. It's like a recommender system, right? Your Google is what? A recommendation engine. Basically, you enter a search query and it recommends different web pages, and it ranks the web pages in a particular order. And this ranking is basically achieved by this algorithm called PageRank. Okay, so that internally uses eigenvectors and eigenvalues. So it is used there, and there are many other applications that are very much a part of this ML literature. So there is every reason for us to study the subject, but yeah, maybe differential equations is not the best motivation, I would say, but still it's a good way to start.
Okay, sir.
Okay, any other?
So that one question, sir, activity question 4.14.
That A transpose A, right? Plus lambda.
Yeah, yeah.
Yeah, I'll get back to you. I'll get back to you. I still don't know the answer, so I need to do some research before I can answer that.
Sir,
Yeah.
sir, thank you very much for the amazing session. It did not feel like it was 2 hours. We were studying maths.
Yeah, thanks a lot, Madhuri. Yeah, so I think you all were a very good audience, so that helps a lot.
Really, thank you a lot, sir, because you have, I have attended your earlier sessions also, and you explained the subject in a very lucid manner. I mean, clearing all the concepts why a particular thing has come out. I mean, beautifully explained, sir. I really appreciate your.
Sir,
Yeah, please go on. Yeah.
question was, you mentioned at one instance that you need to learn NumPy. So can you please suggest some sources where we can start learning NumPy? Like I know very basic of Python, and that's it.
Okay, so NumPy, see in Discourse I shared one resource. MLF. I don't remember where it is. NumPy. Okay, just give me a second. See what we have a NumPy week 0 content in MLT course. Okay, so I mean the course that follows this. Let me see. I don't know, but I'll create a new thread on Discourse and I will add the resources there.
So the resource collateral might have something.
Yeah, that might also have something. MLF resource collateral.
Yeah, it has a linear algebra with NumPy YouTube video by Jaydev, and also a handy intro to NumPy usage in ML.
Okay, yeah. So you can refer to this, Madhuri. This will have. See, there is a multi
under resources.
Under books and you mean
No,
here?
resources after MLP, sir. Yeah, this is also there, and after in resources as well, there are some NumPy resources.
Good. Okay. So you can start with all these things. So there is one thing as Preethadeep mentioned, right? There's one by Jaydev, our student, and
okay. Thank you
right?
very much.
Yeah. Okay. Is there anything else? If not, we'll close the session.
Thank you so much, Karthik.
Yeah.
Thank you, sir.
Yeah.
Thank you, sir. Thank you so much.
Bye bye, everyone.
Thank you, sir.
Bye.
Thanks, everyone. Yeah.
Thank you, sir.